continue our discussion of limits today by talking about how you can find limits algebraically without using graphs or tables of values. Now, most of the time, the function value and the limit are the same. That means most of the time, if you want to find a limit, you can actually just plug the x value in. However, this isn't going to work if when you plug the x value in, you get 0 over 0 or infinity over infinity. We call those indeterminate forms in that those forms don't give us any information about what that limit is. So let's just do some examples. In part A, if I want to find the limit as x goes to 2, the very first thing I always try is I just plug that x value in and see what I get. And so in this case, let's see, 3 times 2 squared minus 2, that becomes 12 minus 2, or 10. And that's my solution. My answer is 10. In fact, the only time that it's not going to work to plug the x values in is when we get one of these indeterminate forms. Okay, example B, if I plug in x equals 6, I end up getting one of those indeterminate forms, 0 over 0. That doesn't give me any information about what this limit is. And so my strategy is going to be to use algebra to try to simplify this thing. And so I'm going to try to factor and see if I can simplify this further. So in the numerator, let's see, to factor I need a product of 6. I think 6 and 1 would work. Make them both negative. That adds up to negative 7. In the denominator, I have a difference of perfect squares. I'll factor that as x plus 6, x minus 6. Now that this thing is in factored form, I can see I have a common factor. I'm going to cancel that out. And I am left with just limit as x goes to 6 of x minus 1 over x plus 6. And now I'm going to try to find this limit by plugging that x value in. If I plug the 6 in, I end up getting 5 over 12. That is not 0 over 0, so that's my final answer here. All right, let's do another example. Limit as x goes to 0 of 3 over x. I start by plugging the 0 in, and I get 3 divided by 0. That's undefined, but it's not indeterminate. We can actually conclude what the limit is. Technically, you could say that this limit doesn't exist because 3 divided by 0 is undefined and it's not indeterminate. However, we can be a little bit more precise here. If I approach x equals 0 from the right, that means I'm actually plugging in very, very tiny numbers that are positive and approaching 0. So 3 divided by something that's approaching 0 is going to be very large. Anytime you divide by something that goes to 0, your answer is going to go to infinity. And it'll be a positive infinity because we're taking a positive 3 divided by a very, very tiny positive number. If I approach x equals 0 from the left, something similar is going to happen. I'm dividing by something very, very close to 0. So my answer is going to grow without bound. However, now I'm taking a positive 3 divided by a very tiny negative number. That's actually going to give me a negative infinity. And so for this reason, the two-sided limit actually doesn't exist because the right hand and the left hand limits are different. Example D. I always start the same way. I plug in 0 for x because I'm finding the limit as x goes to 0. And if I don't get something that's indeterminate, then I know what the answer is. Unfortunately, in this case, it looks like we're getting that indeterminate 0 over 0. In problems like this that have square roots in them, we are going to use a technique called rationalize the numerator in order to simplify. If you want to rationalize, you have to multiply by what's known as the conjugate. So here's my original problem. The conjugate of the numerator is root x plus 4 plus 2. Notice the only difference I made was I changed the sign. Instead of a minus sign, I have a plus sign. I'm going to multiply the denominator by that same thing as well. I have to multiply the top and bottom by the same thing so that the expression remains unchanged. In the numerator, I'm going to use my difference of squares formula. This is why we multiply by the conjugate. If you multiply by two things that only vary by the sign between them, this is our difference of squares formula. We will always get a squared minus b squared. And so in this problem, we are doing exactly this. We are multiplying, and we're going to get a difference of perfect squares. In my example, the a is going to be that root x plus 4, and the b is 2. So the numerator becomes root x plus 4 squared minus 2 squared. And there's not much we can do with the denominator. I'm just going to copy it down as it is. Now if you square a square root, those are inverse operations. You're just left with x minus 4. And then we've got another minus 4. If I combine like terms in the numerator, all I have left is an x, and I still haven't done anything to that denominator yet. Finally, after all of this work, we have a common factor of x, and so I can cancel that common factor of x out. And I'm left with limit as x goes to 0 of 1 over the square root of x plus 4 plus 2. Finally, after you've done your canceling, that's when you want to try to plug your x value in again and see what you get. And so if I plug in x equals 0, I'm no longer going to get that indeterminate form. In fact, I just get 1 over 2 plus 2, or 1/4. And so that's my limit. So anytime we get one of the indeterminate forms and we have a square root in the problem, this is the approach that will work. We can always rationalize, usually it's the numerator, rationalize wherever that square root is. And we do that by multiplying by the conjugate, which is something with the opposite sign. Okay, example E. As always, I always start by plugging my x value of 0 in. And I won't write out the work this time, but guess what? Another indeterminate form. That's kind of the case that happens most frequently. When I see fractions within fractions like this, complex fractions, I'm going to multiply every single term by the LCD to clear the fractions, to get rid of the fractions. And in this case, my LCD needs a 4 and an x plus 4. So I'm going to take everything in the numerator and everything in the denominator and multiply that by the LCD. In the numerator, if I multiply the LCD by the 1/4, the 4's cancel out, and I'm left with that x plus 4. The second term, the x plus 4's cancel out, and I'm just left with the 4. I'm not going to really do anything with the denominator yet. I'm just going to leave it in factored form as 4x, x plus 4. In the numerator, we can get rid of parentheses and combine like terms. And if we do that, the 4's cancel out, they add up to 0, and we're just left with x in the numerator. Finally, I have a common factor of x. I am going to cancel that out, and I'm left with limit as x goes to 0 of 1 over 4 x plus 4. Once we do our canceling, to finish this problem, we are going to plug in x equals 0, and we get 1 over 4 times 4, or 1/16. So anytime we see fractions within fractions, this is our strategy. We're going to try to clear the fractions and simplify as much as possible. My next example is a little bit different in that we have a piecewise defined function. In this function, we are defining the y values to be 2x minus 3 whenever x is not equal to 3. But the y value is negative 2 when x is equal to 3. And so if I want to find the limit as x goes to 3, I don't care about what happens when x equals 3. I only care about what happens when x is close to 3. So when x is something like 3.1 or 2.9. And so if I'm only interested in what happens when x is close to 3, I'm going to plug the 3 into that top definition, because we're thinking about x values like 3.1, 3.01, not actually x equal 3. So I plug 3 into the 2x minus 3. That gives me 6 minus 3, or 3. And so my solution here is 3. So if it helps, I've drawn a picture to show you what's happening here. You don't need to write this down unless this helps. But we basically have the line y equals 2x minus 3, and then there's a hole at x equals 3. So we use the definition of the line for all values of x except for 3. And when x equals 3, then we're at the y value of negative 2. When we're finding the limit, we're on the curve, on the line. We are approaching 3. And I think my scale is a little off on my graph, but that should approach a y value of 3. I'm going to stop this video here and do this video in 2 parts. So we've got just a few more topics left to talk about. We'll pick this up in part 2.